I'll be talking about a problem from hyperplane arrangements, and this is based on joint work with my advisor, Priyavrat Deshpande. Okay, so first we'll start off with the basic background in this topic of hyperplane arrangements. So an arrangement is just a finite collection of affine hyperplanes in some Euclidean space Rn. So affine hyperplane just means an n-1 dimensional subspace or a translate of such a subspace. So for example, in R2, an arrangement is just a finite collection of lines, and these lines need not pass through the origin. Similarly, in R3, it's a collection of planes. The regions of an arrangement are the pieces into which it breaks the space. So for example, this arrangement here breaks up the plane into 6 pieces, and these are the regions of the arrangement. And for an arrangement A, we denote the number of regions by R of A. Now, there is a nice polynomial that you can associate to an arrangement called its characteristic polynomial. And this is just the characteristic polynomial of a certain poset that we associate to an arrangement. And this is its intersection poset. This poset just consists of all the non-empty intersections of hyperplanes in A, ordered by reverse inclusion. And if, like me, you find this definition a bit intimidating, there is good news, which is that you can reduce the computation of this polynomial to a counting problem, which is to mean that for large integer values of t, this chi a of t is just the cardinality of a certain set. And this usually makes the computation of the polynomial much simpler. So we won't really be going into this method. What we'll be focused on is this nice property that you can actually extract the number of regions of the arrangement from this characteristic polynomial. So first off, from the definition, it's not too hard to see. That is, if your arrangement is an Rn, then the characteristic polynomial is one of degree n, and the coefficients are all integers. But what is very nice is that the number of regions is just the sum of the absolute values of these coefficients. So now we have a general problem. You're given an arrangement, you obtain its characteristic polynomial. The coefficients of this polynomial give a breakup of the number of regions. Now, if you know that your regions correspond to certain objects, can you define a statistic on these objects that induces this breakup? So what I mean by this is, suppose you know, say your regions correspond to certain trees. Can I assign to each tree some number from 0 to n, such that the number of trees to which I assigned I is precisely this absolute value of Ci? So we look at a simple example first. The Boolean arrangement in Rn just consists of all the coordinate hyperplanes, xi equal to 0 for all I from 1 to n. Now, any region of this arrangement is just the set of all points in Rn where I fix, okay, these coordinates should be positive and all the remaining should be negative. This is easy to see in R2 and here, and you can also imagine it in R3, but this is true in general. So the regions of this Boolean arrangement correspond to subsets of these numbers from 1 to n. The characteristic polynomial is also not too hard to compute because this is just the Boolean lattice. So remember, the hyperplanes are just xi equal to 0. So all intersections will just be subspaces where certain coordinates are 0. And then it's not too difficult to obtain an isomorphism with the Boolean lattice. And so the characteristic polynomial is just that of the Boolean lattice, which is here, t minus 1 to the n. So we have regions corresponding to subsets. We have this characteristic polynomial from which we can see that the coefficients are just these binomial coefficients. And an obvious statistic that works is number of elements, because the number of subsets that have exactly I elements is precisely this ith coefficient n choose I. So this is the sort of question we'll be dealing with. And now hopefully the title of the talk will make sense, a branch statistic for trees, because what we're going to be looking at is certain arrangements whose regions correspond to trees. We're going to define a branch statistic on those trees. and show that the distribution of this statistic is given by the characteristic polynomial of the arrangement we started with. So the arrangements we'll be looking at are these deformations of the braid arrangement. So for any finite set of integers s, I set a s of n to be the arrangement in Rn with these hyperplanes. So for any I less than j, I have xi minus xj equal to k for all k in S. Now we have this nice result by Bernardi from a few years ago. That is, when S is transitive, which just means S satisfies certain conditions, which I won't be going through. But when S is transitive, the regions of this arrangement, AS of n, is in bijection with a certain set of trees, which I'll call TS of n. And one thing I'll mention is that this transitive condition is not too restrictive in the sense that many popular arrangements of this form, there are these arrangements called the Catalan lineal Xi, their extended versions. All of them are transitive. So this is a fairly general theorem. Okay, now again, I'm not going to explicitly tell you what the trees in TS of n are, but I'll tell you the kinds of trees that are in TS of n. And those are these labeled emery trees. So these are first off rooted trees. So there's a special root vertex, which I'll draw at the bottom. So here 2 is the root. This emery condition just means that any vertex either has no children at all or exactly m children. So this is a two-ary tree or binary tree because every vertex either has 2 or no children at all. And the vertices that have m children, I'll call nodes, and the others I'll call leaves. And if there are n nodes, I will label them using the numbers from 1 to n. So here there were 3 nodes, so I label them using 1, 2, and 3. And another thing is that these are plane trees. So the order of the children does matter. So even though these are just mirror images, they are different trees because here the first child of 2 is a leaf, whereas here the first child of 2 is this node 3. So TS of n is just some set of labeled m-ary trees with n nodes. In fact, this m is fixed for a given s. So for example, this is one arrangement where the regions are labeled by the corresponding trees. In fact, this is one of the popular ones, the Catalan arrangement, s equal to minus 1, 0, 1. Okay, so now we have our question. The regions of AS of n correspond to trees TS of n. Can I find a statistic on these trees whose distribution is given by the characteristic polynomial of this arrangement? Now I'll describe that statistic, but first we need to give names to certain parts of the tree. So first is the trunk. So the trunk just consists of the root, its first child, that thing's first child, that thing's first child, and so on. So you just take this leftmost path in your tree, and all the nodes you meet along the way form the trunk. And we'll use these trunk nodes to break up the tree into twigs, as shown here. So corresponding to a trunk node, the twig consists of the trunk node and all subtrees apart from the first. So you ignore the first child, you include the second child, its children, those things' children, and so on. So this is a binary tree, so the twig is just trunk node and second subtree. But if it were a ternary tree, it will be trunk node, second and third subtree, and so on. And for purely aesthetic reasons, in the last twig, we also include the first subtree, which is just a leaf. And we'll group these twigs together to form branches. And the way we do that is quite simple. So you look at the entire tree, you find the largest node. So here the largest node is 8. All the twigs up to the twig containing 8 form the first branch. So here the first 2 twigs together form the first branch. Now you ignore this first branch. If you want, you can put your hand over it and do exactly the same thing for the rest of the tree. Now in the rest of the tree, the largest node is the one labeled 5. And hence these 2 twigs together form the second branch. And you keep doing this until you break up the entire tree. So this tree has 2 branches. So we look at another example, a ternary tree. And this breaks up into branches just as before. Again, the largest node is 8, which is in the first twig itself. So the first branch is just the first twig. If I ignore the first branch, the rest of the tree has largest node 7. So these two twigs together form the second branch. If I ignore the first and second branches, the rest of the tree is just a single twig, which by itself forms the third branch. So this tree has 3 branches. And the result is that number of branches is a statistic that works. That is, if I look at the coefficient of t to the I in this characteristic polynomial of as of n, it is the number of trees in ts of n that have exactly I branches. So for example, here is some arrangement where the regions are labeled by the corresponding trees. And the characteristic polynomial, if you look at, the coefficient of t cube is 1 because there is exactly one tree with 3 branches. The t square coefficient is 3 because there are exactly 3 trees that have 2 branches. And the remaining 3 trees all have 1 branch, and hence the coefficient of t is 3. So I'll end with a few remarks. So first thing is that, okay, how do you prove this theorem? And the main idea is this concept of exponential structures. So these are structures where, let's say, to give a structure to a finite set, it is the same as partitioning that set and to each block giving a special structure. So for example, permutations. To give a permutation structure to an entire set, just have to partition that set and to each block give single cycle permutation structure. Right? Or you could also think of graphs, the usual simple graphs. And here the corresponding thing would be connected components. And the thing is that branches give trees an exponential structure. And using results about exponential structures can prove this theorem. Now the next thing is, okay, now we have meaning for the coefficients. Can we use this combinatorial meaning to prove certain properties? So that is another question one can think about. And for this particular class of arrangements, we do have certain results like this. And finally, I should mention that in a recent work, we tried to do similar things for other root systems, which essentially just means, okay, till now we had xi minus xj equal to something, but you also include xi plus xj equal to something or xi equal to something. So here we had this very nice result of Bernardi for so many deformations and all. We weren't really able to generalize that. But at least for the Catalan deformations, we do have similar results. So I'll end there and thanks for listening.